Okay, and I will make the third and last attempt to save the notes. If it fails, then I will switch to another system taking notes. But anyway, Alexander Zaitsev can restore the notes even if I cannot save them. So hopefully you will have them this way or another. Okay, so we start studying cohomology. Of sheaves, or more specifically quasi-coherent sheaves. Okay, and then after we develop some general theory, we will return back to the case of curves. Well, then we'll go on to surfaces and so on. Well, the modern understanding is that cohomology of a variety with coefficients in a sheaf. Another notation is like this. Are the higher derived functors of global sections. And well, one of the standard definitions is that the abelian category of abelian sheaves has enough injective objects. This means that an object J is injective if the functor hom from something to J is exact in this something. Okay, and well, the fact is that also what does it mean to have enough? Enough means that for any abelian sheaf F, there is an embedding from F into some injective sheaf. Okay, and then you can somehow iterate such things, so you can produce an injective resolution. So you embed into J, maybe let's call it J.
Можно спросить?
Yes, yes.
Например, в какой категории недостаточно инъективных объектов для таких резольвентов?
An example of abelian category with not enough injective objects?
Да.
That's what you asked? Well, you see, there is some abstract nonsense theorem that any category is essentially a category of modules over some ring. but this ring may be very big, very weird. So there are also, you may impose some finiteness conditions, and then you will not have enough injective objects. Okay, if you want to say some finite dimensional modules over some ring, you will not have, say, over ring of polynomials, just in one variable. Just finite dimensional models over polynomial in one variable. There's an abelian category, but it will not have enough injective objects.
Спасибо.
Welcome. So you have an embedding into J0, and then you want to extend it to an exact complex with injective terms. So the next thing you will have in the quotient J naught mod F, and taken in place of F itself. Okay, so embed now J naught mod F into another, into next injective object J1. Okay, then take the co-kernel of this morphism and embed it into J2 and so on. It does not have to terminate, may be infinite. Okay, so in other words, the only cohomology of this complex J naught to J1 to so on is the zeroth cohomology, and it is just F. In this sense, this J forms a resolution. So maybe it can be also denoted like 0 goes to F goes to J dot. Okay. Only maybe I'd rather use upper indices because dot is an upper index. Okay. Fine. So then there is a basic theorem in homological algebra that any two injective resolutions are homotopically equivalent. And hence have the same well, the resolutions have no cohomology, only H0. So there's nothing to speak about. But if we apply any functor to them, so for any functor F, F of J1 and F of J2 are also homotopically equivalent. I mean, you just take this equivalent between J1 and J2 and apply this functor F to it. Okay, so in particular, they have the same cohomology. So you have this complex. You apply just to term-wise this functor F to the first resolution, and apply the same functor F term-wise to the second resolution, and they have the same cohomology. Okay, and this cohomology, which is independent of a choice of resolution, is the right derived functor. Well, unfortunately, page RIF. Okay, and F is assumed left exact. Okay, so this is the general definition, and then there is another important fact that well, say an object F, well, of our abelian category, that is just a sheaf, is called F acyclic if all the higher the higher derived functors just vanish. Okay, and then the claim is that the cohomology, let's see, sorry, of any object G can be computed.
Не совсем понял, для любого I равного нулю или что это здесь?
Sorry. I is bigger than 0. Sorry. Okay. So the cohomology of any object can be computed via a resolution G goes to F1, F2, and so on, with acyclic terms. So by definition, we have to use the injective resolutions, but in fact the class of resolutions can be significantly extended. Instead of injective objects, you can use any acyclic objects. Okay, so in our applications,
как бы факты, которые мы знаем без доказательства.
yeah, I will not prove this. Yeah, I'm only reminding this. But well, you can go to any standard homological algebra course like Bogorodiantsov or whatever, or look something up in Kempf.
Да, хорошо, спасибо.
So the functor F will be just global sections, and for example, of acyclic objects, you can take Flebby sheaves. Okay, and if you specialize even further, you can take sheaves of discontinuous sections. Discontinuous. Okay, so given any for any abelian sheaf, F, there is an embedding of F into the discontinuous sections sheaf of F. Yeah, if you don't remember it, let me say one word. So you have stocks at all the points, yeah, and you have the product of the stocks over all the points, and then you take somehow the sections to this very big space. Yes, so to any point, you attach any element in the stock over this point. Okay, there is absolutely no relation between values at different points. Okay, and then for obvious reasons, this guy forms a sheaf, and this sheaf is flabby, and have an embedding from F to this thing, and then the advantage of this weird and very big construction is in its canonicity, so to say. Yeah, so we don't have to make any choice. For any sheaf F, you have just this particular sheaf of discrete sections of F. Okay, and there is an embedding from F into this. And then you can iterate it, just as we did with the injective resolutions. Yeah, so you have this embedding from F to discrete sections, and then you take the quotient sheaf, and then you embed this quotient sheaf into the next, into its own discrete sections sheaf, and so on.
А это вложение как диагональное, то есть вот discrete sections, он содержит бесконечное произведение разков, и мы вкладываем просто как диагональ.
Yes.
Спасибо.
So we can call it ds0, and then it goes to ds1, it goes to ds2, and so on. So here, well, let me just write it, that ds1 of F is ds of the quotient sheaf, ds of F modulo F, and so on. So I have this resolution, Flabby resolution.
В факторе подразумевается, что F как бы вложено уже в DS.
Oh yes, it is. Yes, there is a as you said yourself, there is a canonical, so to say, diagonal embedding from F to discrete sections of F sheaf. Okay. So this is very, very big. Absolutely, you cannot keep any control over this. So the only advantage of it is in its canonicity. So it's a canonical Flabby resolution. And then, for example, Kempf defines cohomology via this resolution. Cohomology of F is the cohomology of global sections.
Первые когомологии в DS0 лежат, например, чтобы обозначение понимать.
Yes. So you replace F by its resolution as I wrote here. So it starts with DS0, then goes to DS1, and so on. Okay, and it's isomorphic, well, quasi-isomorphic to F. So the only cohomology is the zeroth cohomology, and it's equal to F. Okay, so we take global sections of this thing. And that's the definition. But as I explained, it is the same as the standard definition via injective resolution, using this fact too, because all Flabby sheaves are acyclic. They don't have higher cohomology. Okay, so maybe let me also formulate some basic properties without going to their proofs. So the first follows from the snake lemma. So if you have an exact sequence of sheaves, like this, then it gives rise to a long exact sequence of cohomology. So it's left exact, so it starts from 0. And the zeroth cohomology is just global sections. then it goes to the zeroth cohomology of G, which is again the same as global section. Sorry. Then it goes to zeroth cohomology of H, and then there is some boundary homomorphism to H1 of X with coefficients in F. Then it goes to H1 with coefficients in G, then H1 with coefficients in H, and then again there is another boundary homomorphism to H2 with coefficients in F, and so on. And this is a long exact sequence, so we'll use it all the time. What else? Also, we'll use that the cohomology commutes with colimits, direct limits. Okay, and maybe that's enough of basic properties. And now the next big theorem we're going to prove is that the theorem of Jean-Pierre Serre, and it was proved in I think 1955, right after he introduced quasi-coherent sheaves, that if X is an affine variety, and F a quasi-coherent sheaf, then there are no higher cohomology. Okay, and somehow this could be expected, because if you remember, we proved that the category of quasi-coherent sheaves on an affine variety is equivalent to the category of modules over the ring of regular functions on X, and the equivalence is given by global sections. In particular, this global sections function is exact. Okay, and since it's exact, it has no higher direct images, and well, so the higher cohomology vanish. And there's a sort of slogan. Now we will prove it rigorously, but the idea is like this. Okay, so first we will use some technical proposition, well, with the slogan of effaceability, that somehow all the global cohomology classes are locally local. Well, they locally vanish, and in Russian it's called стираемые. In French it's effaçable, and in English it's also effaceable, taken from French. Maybe let me. Write it like this. So let me have a basis of topology. New of open set in some variety X, not necessarily affine. And now assume that for some sheaf, the cohomology, sorry, but not of the whole X, but of these open sets with coefficients in F are 0 for any index J between 0 and some other index I. So I is fixed. Okay. And then for any class sigma in the jth cohomology, sorry, in ith cohomology, global cohomology of X with coefficients in F, there is an open covering. And this open covering is in this basis of open sets. So double alpha belongs, so to say, and such that the restriction of this class to all the open subsets is 0. Let's say the restriction of sigma to any W alpha is 0. Okay, so this is called the effaceability. So when you, this class itself is not necessarily 0, but when you restrict it to any open subset in our basis, you get 0.
Ну, такое сигма, ну, такое покрытие существует, что сигма на этих покрытиях равно нулю.
You ask how to prove this proposition? We'll prove it right now.
Понятно, спасибо.
Okay. Okay. And maybe equivalently. Well, let's for this open subset in X, we denote by JW alpha, or maybe J alpha, its open embedding. And then we have a morphism from F into the direct image of the restriction to this open subset. And well, there is such a canonical adjunction morphism. And well, I don't know how to call it. Maybe M, because it's a morphism. So I claim that M of sigma is 0. It's the same as the restriction of this cohomology class to this open subset is 0. Okay, so let's prove this. And the proof will take more than this page. But how to say, it's not difficult, but you have to write down something. So first, we will do this by induction in I. Sorry. I is you see that the number of cohomology below which all the cohomology of our basic open sets vanish. Okay, but for I we don't know yet, and we have to prove it for I. So we start with I equals 1, and then we have no assumption whatsoever. You see, we assumed something for j smaller than I, but bigger than 0. So for I equals 1, there is no assumption whatsoever. And we have to prove that all the first cohomology classes are effaceable, okay, without any assumption. One classes. Okay. So we have this canonical resolution. Let's write its beginning. Goes to discontinuous sections of F, goes to the quotient, and there's a short exact sequence of sheaves. And now let's also take this embedding into J W, the push forward of the pullback of F, and do the same with the discrete sections sheaf. And also do the same with the quotient.
Зачем еще pullback брать?
Pardon me?
Почему нельзя просто написать, ну, уже со звездочкой внизу F? Ведь это F.
Well, I would vote for this. Yeah, if nobody objects, I would do this. But for formally, you first have to restrict your shift to this open and then push it forward back to the whole of X. But this restriction to the open is if it's tacitly assumed, then you can never actually write it. So I will have left to right, so I would vote for this. Okay, so have this commutative diagram, and now let's take any section, any class in the first cohomology, and well, but by definition, it is represented by a global section of the quotient sheaf of discrete sections modulo F on the whole of X. Yeah, just if you apply the long exact sequence of cohomology to the short exact sequence, F goes to the DSF goes to the quotient. Since DSF is flabby and does not have any H1, yeah, any H1 of F comes from global section of this quotient, DSF modulo. It's just from the long exact sequence of cohomology, because DSF is acyclic. Okay, so we can find the covering.
Сигма равно нулю, потому что DS вялый, DS от F. Так или что-то другое сказать?
No, sigma. No, I don't claim it's 0. It's not 0. I will prove that it's locally 0. I didn't prove it yet. And it is too bright sun, Altan. You seem unhappy because the sun is too bright, no?
Yeah, the sun is really bright, but I am trying to understand whether the slogan, just our slogan, which you stated, works for us, because for factor of global shifts, global sections is exact, and we are done with proving the Serre's theorem.
No, No. We do have to prove something. It's not automatic. We will use this proposition.
And I'm trying to understand why, because global sections, the functor of global sections is exact, and then.
And so what? It's only exact on quasi-coherent sheaves. But if you take, say, injective or these discrete sections sheaves, flat sheaves, they will not be automatically quasi-coherent. So there is something to prove. You see, our formal definition of cohomology takes us out of category of quasi-coherent sheaf.
Okay.
A priori, there is something to check. So where are we? We can find the covering by these basic sets, the union of V alpha, such that well, this global section, let's denote it, say, by tau, such that this global section tau, when restricted to any covering open set, lifts to a section of discrete sections sheaf over V alpha. Yeah, just because this is an exact sequence of sheaves, and so locally any section of the quotient sheaf can be lifted to the section of the middle sheaf. Okay, and hence for any this alpha, for any open set V alpha, the image of this lift tau in the global sections with coefficients in J alpha, push forward J alpha, pull back of ds of f, modular J alpha, push forward J alpha, pull back of f itself, lift to a section of J alpha, push forward J alpha, pull back ds of f over the whole x. Okay, but since it does, it means that the image of sigma of our original section in the first cohomology of x with coefficients in J alpha, push forward J alpha, pull back f is 0.
Могли бы вы объяснить последний переход?
Если
поднимается, то
but just again from the long exact sequence of cohomology, yeah, if something where were we here? Yeah, you see, if something comes from so look at this basic property 1. Yeah, you have this long exact sequence of cohomology. If something comes here, yeah, if a global section of H comes from a global section of G, yeah, the middle sheaf, then the connecting homomorphism to the first cohomology of F must be 0 because it's a long exact sequence. Yeah.
Спасибо.
Okay. So we proved we proved the base. Okay. Now we'll move to Sorry. We'll prove to I bigger than 1. What did I do? Something is wrong. Okay. I is bigger than 1. And then we will use the small lemma. So first, I claim that there is a commutative diagram of exact with exact rows. Just as we used before. F. And here you have the push forward of the pullback of F. Now the same applied to discontinuous sections. And now the same applied to this quotient. Okay, so here J is an embedding from some basic open set into X. Okay, and also we claim that the quotient sheaf ds of F modulo F satisfies the assumptions of the proposition with I that is just a little bit smaller. Okay, and this is so let's prove this lemma. So
первым
yes.
утверждением мы уже не пользовались, оно же уже доказано или нет?
The difference is that you apply this pull push to the quotient sheaf. Yeah. Before what we did, we in this diagram, yeah, we apply it to well, you see, there's a different thing. We apply it to the discrete sections and to F itself, and then we take the quotient. And here instead, I apply pull push to the quotient. Okay, that's different with what we had before. Okay, so let's take any. Well, just the sections of this. Of the bottom row over any open set V in our base R are what? The global sections of the intersection with W, and it goes to global sections intersection with W over discrete sections, and it goes to global sections over the intersection with coefficients in the quotient sheaf, like this, well, it's left. Sorry, it's left exact, but the problem is why is it exact in the right term? Yeah, but then in the right term, you would have the first cohomology, right? But so the abstraction to exactness on the right is the first cohomology of this intersection with coefficients in F, but this intersection is also a member of our base of open sets, right? And by assumption, since I is bigger than 1, the first cohomology must vanish. Okay, so if you recall the statement of the proposition, yeah, we assume that all the cohomology of our basic open sets for j less than I were 0, and now I is bigger than 1, so in particular j equals 1 works. Okay, and this cohomology vanish. Fine, we proved A. Now for B, we know that we have the isomorphisms of this cohomology. Right, or any positive j, just because the difference is in cohomology of DSF, and DSF is flabby and does not have any higher cohomology whatsoever. Well, okay, so the lemma is proved, and now let's have one last look at this lemma, because now I'm going to use it to finish the proof of proposition. Okay, well, so the idea will be to replace our f by this quotient ds of f modulo f, and then use the induction assumption. Okay, and we are ready to do this. Finish the proof proposition. Just we say that the I minus first cohomology with coefficients in this quotient are isomorphic to the ith cohomology with coefficients in F just by the boundary isomorphism, and we have the commutative diagram. Here we have minus first cohomology with coefficients in the push-pull of this. Okay, and it's also isomorphic to the ith cohomology with coefficient in the push-pull of F. Yeah, maybe like this. Again, this is true since I is bigger than 1, and we can go one down, and that's it. That's exactly what I wanted to prove. Yeah, so I can replace my sheaf F by DSF modulo F. Okay, and then it will replace I by I minus 1, and I can proceed by induction. Okay. Fine. So finally, we are able to prove this theorem by Serre. And so we want to prove that the higher cohomology of quasi-coherent sheaves on affine varieties vanish. Okay, and again we prove this by induction. So we will apply this proposition. So for a base of our topology, we'll take the basic open subsets. Df. F is a regular function on X. And now we'll use the method of bootstrapping. So we will use that all those basic sets are also affine. Okay. So if you remember, when we proved the proposition for I equals 1, we use nothing, right? Well, let's go back. Yeah, you see here we started with the base I equals 1. There was no assumption because there was no j that is bigger than 0 but smaller than I, and we use nothing. And here again we will use nothing for I equals 1. So we'll prove something, but it will work for any affine variety. So starting from nothing, we'll prove that the H1 vanishes for any affine variety, in particular for all those basic open sets DF. And then we will use this to go to I equals 2 in our proposition, because we'll know that for all the basic sets DF, the first cohomology already vanished. Okay, and that's the bootstrapping method. So we take some cohomology class. And find an open covering B F1 and so on, D sorry, D of n, such that sigma restricted to the F, sorry, I is bad, to df k is 0 or any k. Okay, and now take the exact sequence. 0 goes to f, goes to the sum from k equals 1 to n of j k push forward, j k pull back of f, and then there is some quotient. And this quotient is necessarily also quasi-coherent. Okay. So we know that our class sigma must be the boundary homomorphism of some class tau for minus first cohomology with coefficients in G. And now if I was bigger than 1, then by induction we may assume that tau is 0, and hence sigma is also 0. And if I is 1, then we know that the global sections with coefficients in quasi-coherent sheaves are exact. And hence
Почему она точная
we have.
будет?
Pardon me?
Почему точная будет последовательность, если мы
We
возьмем...
proved this when we studied quasi-coherent sheaves, that the global sections on quasi-coherent sheaves are exact.
Спасибо.
This was some basic property of quasi-coherent sheaves. So we have 0 to global sections of X with coefficients in F, then global sections of X with coefficients in this direct sum of J, K push, J, K pull, and then to global sections with coefficients in G, and then there is this boundary homomorphism to H1 of X with coefficients in F, but because this global section, because this sequence of gammas was exact, the boundary homomorphism is necessarily 0. And in particular means that sigma is delta tau is 0. Okay. Okay. So once again, it's a bootstrapping. We just proved that any first cohomology class of F is 0. Then we apply it to all the open subsets, the basic subsets, and then we use proposition to prove that the second cohomology class of F is also 0, and you apply it to all DFs and so on. Okay. So again, we're done by induction. Okay. So now let's move to higher direct images of quasi-coherent sheaves. But first, let's prove the following corollary of Serre theorem. So we take an affine morphism of varieties from X to Y affine morphism. And F a quasi-coherent sheaf on X. So then I claim that for any I, the cohomology with coefficients in a quasi-coherent sheaf are equal. Oops, sorry. What happened? Strange. Sorry. For some reason, my stylus stopped writing. Oh, good. It is equal to the cohomology of Y with coefficients in the push forward, sorry, of F. Okay. So let's prove this. Let's take any Flavor resolution, so say ds. F goes to ds bullet of F, a Flavor resolution. And then recall that the push forward of a Flavor sheaf is again a Flavor sheaf. So we can use it to compute downstairs on Y. So for any open, say V in Y, we have a resolution. You take global sections of the pre-image of this open set with coefficients in F, and you can also, and on the other hand, you take the global sections of this resolution. Okay, so this is exact since the pre-image of V is affine, and by Serre's theorem, okay, but it means that the push forward of the DSF is a Flavor resolution of the push forward of F. Okay, and then we can compute the cohomology via this Flavor resolution. Okay, the cohomology of the push forward of F is the ith cohomology of global sections of Y with coefficients on the push forward of the Flavor resolution. And this is the ith cohomology of global sections of X with coefficients in this resolution. just because the global sections well, compose with the push forward. Global sections on Y composed with push forward are global sections on X. Okay, and this is by definition. By definition, the ith cohomology of our sheet. Okay, there we are, and now this can be phrased as follows: that the reason is that the higher direct images are all zero for affine morphisms. Okay, so we started today with the definition of derived functors. Okay, so then we used it for functor f equals to global sections. Well, global sections of something, and then there are right derived functors are gamma I. That is just the global cohomology, and it can be computed via injective or Flaby or any acyclic resolutions. Okay, and now we just apply the same strategy to another functor. So now I take f, just the functor of push forward. Okay, from sheaves on X to sheaves on Y. Okay, and again we can, since Flaby sheaves go to Flaby sheaves, and the exact sequence of Flaby sheaves go to exact sequence of Flaby sheaves for this push forward. We can use Flaby sheaves to just the same Flaby resolutions can be used to compute the higher direct images of push forward from X to Y. Okay, and well, say one thing that follows immediately is that the well, first of all, the zeroth direct image functor is just pi star itself, and the higher ones is the sheaf. Well, is the sheafification of the pre-sheaf, which associate to any open subset the higher cohomology of its pre-image with coefficients in F. Okay. And also there is a long exact sequence. So if I have 0 to F to G to H, then we'll have
пучковизация. Почему это не будет пучком?
Well, I don't know, for higher cohomology, it may not glue automatically. So you'll have 0 to 0 direct image f that is the same as just direct image of f. Then to the 0th direct image of g, then to the 0th direct image of h, and then there is the boundary homomorphism to the first direct image of f, and then natural morphism to the first direct image of g, and then to the first direct image, of h, and then there will be boundary homomorphism to the second direct image of f, and so on. So formally, there is no difference, and in fact, for any derived function, there will be the same situation. Okay, but now well, in fact, this is the same argument in this as in the proof of the previous corollary. Proves the following. Well, in fact, we just proved exactly proved this. So we proved, well, we had this corollary that for a fine morphism, the cohomology of x can be computed as cohomology of the push forward on the base y. Okay, and then I said that the reason is that there is no higher direct images for quasi-coherent sheaves for a fine morphism. Okay, and now I just state this formally, that if pi from x to y is affine, and f a quasi-coherent sheaf on x, then there are no higher direct images on y. Okay, just the proof I gave of the previous corollary, it actually proves this result. Okay, so now x is the morphism is not supposed to be affine anymore. So we can have higher direct images, but I will prove that all those higher direct images are still quasi-coherent sheaves. If you remember, we proved this for the 0 direct image. Yeah, so just the direct image of a quasi-coherent sheaf is quasi-coherent. We proved this in November or December, and now we prove the same thing for higher direct image. Okay, so we have pi from x to y, and f quasi-coherent, but we don't assume pi to be affine anymore. And then all the higher direct images of f are quasi-coherent, and more precisely, for any open set in y, the cohomology of the with pre-image in x with coefficients in f, this is a module over the regular functions on v. Okay, maybe let's assume that it's affine. So we take an affine open subset in y, then take the cohomology of its pre-image. Certainly, there is an action of regular function on y on this pre-image, and so we can localize this module over the regular function on y to obtain a quasi-coherent sheaf on v. Okay, and then there's nothing but the restriction of ith direct image to V. Well, in particular, BB certainly implies A, so we have to prove B. Okay. Now this is a local statement over Y. So we can assume that Y is affine. And then we have, as I just, well, okay, we have a map from cohomology of X to the global sections of Y with coefficients in the direct image of F. Okay, and also the regular functions on Y act on everything here, both on cohomology on X and on the global sections on Y, and so we obtain just by adjunction a homomorphism from localization like this to the sheaf. So now we have to check that this homomorphism is an isomorphism of sheaves. Okay, and let's check this at stock-wide. At Y at a point in the base. So we have to check that the localization with respect to the maximal ideal of this point is isomorphic to the stock of this sheaf. That is a limit over smaller and smaller neighborhoods. Okay. So V is a neighborhood containing Y. Okay. And our Y was affine, so the neighborhoods can be taken as basic open sets, and then what we have to check is that for any F, a regular function on Y, that the localization of global cohomology with respect to this F is the same. Well, is the same as the cohomology of well, how to say it, by inverse of df with coefficients in F. Okay, so the inclusion from by inverse df into X is an affine inclusion.
Вот последний изоморфизм, почему так получился?
No, we only have to check. I just explained what we're really checking. We didn't prove it yet. We only have to check this.
Понятно,
It's
спасибо.
enough to check this. Okay. Did I answer your question?
Все, спасибо, понял.
Okay. Yes. Okay. So this embedding of this the preimage of df, because it's just given by non-vanishing of function f. This function f was on the base, but since we have this morphism, well, let me write it down. This is also d f composed with pi, so to say. Yeah. So it's a sort of basic open subset in X. Okay, so it's an affine embedding, and as we just seen in the corollary, the cohomology of pi inverse df with coefficients in f are the cohomology of X with coefficients in push-pull f, where j, well, let me know here. This is j. Okay. Okay. So now f is quasi-coherent, and hence this push-pull is the direct limit of 1 over f to the power n. Yeah, well, I'm afraid you don't remember it anymore, but we had such a theorem, a basic theorem about quasi-coherent sheaves. So an important isomorphism and well, a basic property of quasi-coherent sheaves. So you may look it up in December or November lectures. Okay, but now we know that cohomology commutes with colimits. Okay, and so we're done. So the cohomology of X with coefficients in push-pull f equals the limit of cohomology of X with coefficients in f, and this is just the localization this of X of cohomology with respect to f. Okay, there we are. Okay, so that's it for today, and next time I hope we'll finish with the general cohomology theory and start applying it to curves. And now I'm afraid to try to save my notes, but let me try. Okay, so I will let you know soon of my success or failure.
Можно спросить?
Yes, yes.
Вот в самом начале мы сказали, что мы работаем в абелевой категории абелевых пучков. А что есть, например, не абелевая категория абелевых пучков?
No, I mean that this general formalism of derived functors applies to any functor from one abelian category to another abelian category. And we apply it to the example. As an example of abelian category, we consider abelian sheaves on a topological space.
Понятно, спасибо.
Welcome. So if there are no more questions, then I will stop the recording.